there's a lot more up here for objectives, but we're not going to get through that today. So what we're going to do is we're going to be able to talk about using long division and the division algorithm. I really didn't want to get started on a lot of this anyway, since we're going to have a week off. I don't want anybody starting to forget anything. Although you guys seem to have just memories made of gold, because you're always picking up on little pieces here and there. So use the remainder and factor theorems, use the rational zero theorems, find the upper and lower bounds, all when we come back from break. I know. I hate having to wait to teach you that stuff, but we'll get there, just a matter of time. So, we'll start with this. Do we remember how to do long division? Just normal long division. So, we take a look at this and we see, hey, there's some vocab here. When we use this format, this is called the dividend. What's underneath that division symbol? And then the divisor is, hey, what are we dividing by out here? And the answer, you're going to recognize that word as a math word. Fancy math word for division is quotient. So that's what we get when we're all done. So we start by saying to ourselves, okay, let's see, how did this work again? I'd first look at the 3, but 32 won't go into 3. So that doesn't make any sense. I shouldn't just look at the 3. I should look at the next digit as well, 35. So 32 does go into 35 once. Oh, and then what did you do with 32? Well, there's not a minus there. It's just what you do, you subtract. Yeah, that's important to remember. We know we're supposed to subtract. With polynomials, we're going to talk about adding a negative instead, because it'll allow us to keep track of things a little better. But yeah, we're supposed to subtract. And when we do that, we get a 3. Same problem. 32 won't go into 3. You remember what you do?
Bring down the 8.
That's what you do. Bring down the next number. Bring down that next digit. 32 goes into 38 once. All right, so 32, that gives me a 6. 32 won't go into 6. So what do? Bring down the 7. We keep bringing down stuff till we just can't bring it down anymore. And then we notice, hey, I can multiply that by 2 this time. And now I have a 3. And I don't have anything else to bring down. So what do? Yeah, this is the remainder. You know, we don't just start making stuff up. That's not going to work. That's a remainder. So it will be plus 3 over 32. So the answer is 112 plus 3 over 32. And yeah, I write big, so my remainder's down there. But that's what you do with long division. And that really is the same kind of thinking we use to do long division of polynomials. We use the same thinking. So we come down here and it says we're going to make it interesting. Not just division, but polynomial division. But we do want to set it up the same way. So we're going to go ahead and make our division symbol and put our 3x cubed plus 5x squared plus 8x plus 7 in the position of the dividend. We're going to put the 3x plus 2 out here in front as our divisor, and we're going to find the quotient. But the difference is we do polynomial long division by just focusing on the first term. Always just the first term. In normal long division, if the first term wasn't enough, we'd use the first and second terms. But in this case, here's what we do. We say, all right, I have a 3x plus 2. If I'm going to get rid of anything, the first thing I want to get rid of is that term right there. So I figure out what would I have to multiply 3x plus 2 by. And I don't really care about the plus 2 in the back. I need the first term to be 3x cubed. So what would I have to multiply 3x by? That's it. X squared? X squared it is. But here's what we also know. In algebra, you can't just do something to part of an expression. We're going to have to multiply that by the 2 as well. We're going to have to distribute that. So over here, we now know we will have 3x cubed, and then x squared plus 2 is 2x squared. But now, you had mentioned before, you always know you're supposed to subtract. And like I said, to keep track of things with polynomial long division, it's easier to think of it as adding a negative, so usually we'll just change the signs and add. But before I do that, I want to think, did this work? Is this going to get rid of my first term? Yeah. So this x squared, that was good stuff. I'm going to line that up right with the other x squareds. I mean, that's part of organization in math, is just keeping things all lined up, get those nice vertical lines of things going on here. So now we go ahead and do, via adding a negative, 3x cubed is gone. That's exactly what we wanted to achieve. 5x squared minus 2x squared will be 3x squared. And, as you told me before, we bring the next term down. So now, we're back over here with our 3x plus 2. And we only focus on the first term. So what are we going to multiply that by? Just x this time? Okay. So x times 3x, yep, that'll give us 3x squared. And then x times 2 plus 2x. Looks like it's going to work. I'm going to put my x up here. But what do I have to do? Change the signs. And add. 3x squared minus 3x squared, gone. Perfect. That's what we wanted. 8x minus 2x is 6x. Done? Don't know yet. Got to bring the 7 down. Haven't dealt with that 7 yet. All right. So I have 3x plus 2, and I have to get rid of the first term. What should I multiply by? Okay, let's multiply by 2. See what happens. 6x plus 4. Hey, that worked. I'm going to put my little 2 up here. There it is. Change my signs. Add. And I get 3. Do we have anything else to bring down? Is there some way we could take 3x plus 2 and multiply it by something and get 3? Then that's our remainder. So this is plus 3 over 3x plus 2. Remainder over the divisor. And that's exactly how we did this last year. Exactly how we did polynomial long division. So, I always like to know, is my answer right? For just about everything in math, what we do forward, we do backwards. So I think, okay, this was division. That's what I did here to get this. So the inverse of division, to check it, would be multiplication. So we should be able to check it and make sure that it's going to work. I mean, we just said this division works. So multiplying 3x plus 2 times x squared plus x plus 2 with the remainder, adding 3, should give us 3x cubed plus 5x squared plus 8x plus 7. We need to check that out. So we're just going to do that with the one problem. We're not going to do it with the numbers. That would just be kind of silly. So we're going to do our 3x plus 2 times our x squared plus x plus 2. And we said it didn't work out perfect. We had a little plus 3. And we want to check and see, will we get that dividend back? I mean, that's the way to know whether or not we did it right or not. That's what we always want to know. So we would have to distribute the 3x through the parentheses over here and get 3x cubed plus 3x squared plus 6x. Then we'd have to distribute the 2 through the parentheses, so plus 2x squared plus 2x plus 4, but then don't forget our little plus 3 remainder that we had in the back. And then it's time to combine like terms. Okay, well, 3x cubed is the only x cubed term, so that's gone. 3x squared and 2x squared is 5x squared. 6x and 2x is 8x. 4 and 3, 7. Go back, flip back. And our dividend was 3x cubed plus 5x squared plus 8x plus 7. Yes, we're good. We got it. You know, whatever we do forwards, we want to be able to do backwards to make sure that we've done it right. Now, we have just found ourselves another way to write our answer. That's another way to write what happened when we did our division. We say, you know what? if I wanted to check this out, what I really have to do is multiply divisor, dividend back together and add my remainder, and that will get me what I need. So we have two different ways. One's called the summary way, and that's the one that we're used to, and then we have one as a product here. So down in this little box of important stuff, division algorithm for polynomials, a lot of function notation. It says let f of x and d of x be polynomials with the degree of f greater than or equal to the degree of d. Oh, so they're saying that's important. That if this is x squared and this is x, we're kind of out of luck. Yeah, we know that. You know, we have to have that degree higher so we could actually do the division to start off with. And then it says d of x cannot equal 0. Okay, makes sense. Then there are unique polynomials q of x and r of x called the quotient. That was what we had on top of our division symbol. Such that when we multiply them back together and add the remainder, r of x is the remainder, we should get our dividend right back. And that says where either r of x equals 0 or the degree of r is less than the degree of d, where we have to stop because we can't do the division anymore, you know. And every once in a while the remainder will be 0 because it'll divide into it perfectly. You know, that happens. We like it when that happens. So f of x in the division algorithm is the dividend, and d of x is the divisor. So we go ahead and do that division, and if r of x equals 0, we say that d of x divides evenly into f of x. No remainder, dividing evenly. So down here, this is the summary statement, and this is how we've been writing our answers. The summary statement in the division algorithm will sometimes be written in fraction form. You're taking some polynomial and dividing it by another polynomial. You're going to get your quotient, q of x. In a lot of cases, you will have a remainder, so you'll put your remainder over that divisor. That's how it always works. That's the way we're used to writing our answers. So this is how what we did would be summarized. We did this division. 3x cubed plus 5x squared plus 8x plus 7 divided by 3x plus 2. And our answer was x squared plus x plus 2 plus 3 over 3x plus 2. So that's the summary statement. And example 1 says, let's use some polynomial long division and find the quotient and the remainder, but we're going to write it both ways. We're going to write a summary statement in the polynomial and in the fraction form. So let's see here. I have 2x to the 4th minus x to the 3rd. Wait a minute. What happened to the x squared? And the x dropped all the way down to -2. When that happens, it's a good idea to put some placeholders in. So we put in here plus 0x squared plus 0x minus 2. It just makes it a lot easier to keep track of what you have. And some of these can get pretty involved, so the more you can keep track of, the better. And we have this nasty little trinomial out in front that wants to be divided into that. 2x squared plus x plus 1. All right, reminder, you don't focus on the whole thing. You don't try to do it all at once. You take that 2x squared plus x plus 1 and you think, how do I get 2x squared to be 2x to the 4th? What do? Multiply by x squared. So that will give us 2x to the 4th plus x cubed plus x squared. Now again, I can see it's lining up. It's going to work, so I'm going to go ahead and write my x squared up there. But then what's the next step? Yeah, so changing those signs and adding, which is really our subtraction. So 2x to the 4th minus 2x to the 4th, we knew that was going to happen. Negative x cubed minus x cubed, negative 2x cubed, and then we have a negative x squared. Well, normally we bring down the next term. It's just kind of weird this time because it's going to be a 0x, but it's still the next term. So now we have 2x squared plus x plus 1. How are we going to get that to match up? Negative 1? Negative x. Will that take care of both issues? Okay, so negative x. because then we'll have negative 2x cubed, which will match that up. But the rest of it has to be multiplied too. So negative x times x, negative x squared. Negative x times 1, negative x. It's working. So I'm going to put my little minus x in here. And then change the signs and add. So negative 2x plus 2x cubed, gone. Negative x squared plus x squared, gone. 0x plus x is x. Bring down the negative 2. Can we multiply 2x squared plus x plus 1 times something to make it x minus 2? No. We've just found our remainder. So this will be plus x minus 2 over 2x squared plus x plus 1. And now what we want to do is write our answer in both forms. So I'm going to scroll up here, which means I'm going to lose some of this. Originally, our problem was 2x to the 4th minus x cubed minus 2. We were dividing that by 2x squared plus x plus 1. And what we got was our answer up there a second ago, which was x squared minus x. And then we had our remainder plus x minus 2 over 2x squared plus x plus 1, our divisor. But now the new piece we want to tack on is, hey, if we're going to check this, what would this look like? What pieces would we multiply back together, everybody? What do we multiply? Okay, so we're going to need a 2x squared plus x plus 1, the divisor, quotient, and what was the last important part? Add the remainder. On the next page we see an important case of the division algorithm occurs when the divisor is of the form d of x equals x minus k, where k is a real number. So notice we have 1x, x minus k. That should make us think a little bit about the fact that whenever we've been working with transformations, we'll use that whole x minus h. And it doesn't really matter too much if we're using an h or a k. But it says where k is a real number, and because the degree of d of x equals x minus k is going to be 1, the remainder is a real number. So what does that tell us? If we take our d of x and we multiply that by q of x and add the remainder, we get what we originally started with, which is exactly what we've been doing when we are writing these out. So evaluating x equals k yields, well, if we take this x and we replace it with a k, and that's what's going on right here, it'll say k minus k times our quotient plus r. Well, k minus k is 0, so 0 times the quotient plus the remainder means all that we're going to have left is the remainder. So they're saying if we evaluate this for that 0 that we have, we'll just get the remainder. So like it says down here, f of k equals r, which is the remainder. So the remainder theorem says if the polynomial f of x is divided by x minus k, then the remainder is r equals f of k. Well, yeah. So if you put k into this function, as we saw up there, we're going to end up with a 0, and the only thing that will be left is that addition of the remainder. So this enables us to find the remainder of a polynomial when it is divisible by x minus k. So what does this mean? It means we're going to be able to use some shortcuts for things, and that would be when we have an x to the first with a minus k behind it. And in this case, if we just want to figure out what the remainder is, that means we find the 0 and we substitute that in to get the remainder. Well, the 0 of x minus 2 is going to be 2. So if we can figure out f of 2, then we'll have the remainder. So all we have to do is put a 2 in for x, 3 times 2 squared plus 7 times 2 minus 20, and we'll have f of 2. And you have to follow the order of operations. So 2 squared is 4, 3 times 4 is 12, 12 plus 14 is 26, and 26 minus 20 is 6. So we have the remainder there for f of 2 because this is an x minus k format. That's the reason we can do this to find the remainder. For x plus 1, we'd want to find f of negative 1. So 3 times negative 1 squared plus 7 times negative 1 minus 20. Well, negative 1 squared is 1. 3 times 1 is 3. 3 minus 7 is negative 4. Negative 4 minus 20 is negative 24. And that would be the remainder for x plus 1. And then the last one, x plus 4, again, we're talking about first degree in that x minus k format. The 0 would be negative 4. So we would have 3 times, I should write f of negative 4 first, 3 times negative 4 squared plus 7 times negative 4 minus 20. Negative 4 squared is 16, so we'd have 3 times 16, which is 48. 7 times negative 4 is negative 28, so that's 20, and 20 minus 20 is 0. Now that is even bigger than the results that we had for A and B, because what that tells me is x plus 4 is a divisor of 3x squared plus 7x minus 20. And how I know that is because it had a remainder of 0. So when we get a remainder of 0, that is really significant. It tells us that this was factorable. So that's why it's important and helpful. A remainder of 0 means you have a factor. And when we have that, that's important for us for finding the 0. So if we can find a remainder of 0, it means that the factor x minus k divides evenly into our polynomial. This indicates that k is a solution, and also graphically an x-intercept of the graph of the polynomial. So down here it says using the table feature of the calculator helps us to find the remainders of several division problems at once. And you'll notice here that they went ahead and graphed the 3x squared plus 7x minus 20 that we were just using in this problem. And you'll also see that the values that we obtained are right here. So at 2, we see that there's a 6 for a remainder there as the y sub 1. And then we also look at negative 1, which came out to negative 24. And then, of course, the one that's of the most mathematical use to us right there would be negative 4, 0. So that is also an intercept of the graph. So notice all they did was graph the original, 3x squared plus 7x minus 20, and then use the y's to figure out what those remainders would be, because that's what they are. So connecting all of this together, we know that this is special. And we can use that and say, you know what, let's just use the remainder theorem here and figure out, after everything else is divided, what the remainder is going to be. And that remainder becomes these values that we see right here. So that's the connection between the math we're doing and the visual of the graph. And then for another theorem, we have a factor theorem, and it says a polynomial function f of x has a factor x minus k if and only if f of k equals 0. And we knew this in Algebra 2, so this is just review, and we're just still making our way through all of those objectives that we had at the beginning, and we're still using long division and the division algorithm, and we've just talked about the remainder theorem, so now we need to talk about the factor theorem. But we need to be able to apply that to what it is we're going to be doing mathematically. So it says, using the ideas of the factor theorem, we can take a new look at example 2. And it says we have a known factor of x plus 4. So if you go back to example 2, you'll see that we had the 3x squared plus 7x minus 20. And the one that we were really interested in is the one that had the remainder of 0, which is this one right here, which is the x plus 4. So if we want to see what's so interesting about that, what we would do is take that polynomial of 3x squared plus 7x minus 20 and divide it by x plus 4. Because again, when we went through this, we saw there was a remainder of 0, which means this should work out perfectly when we go through this. So if we have x plus 4, and we need that to match the first term of 3x squared, we're going to need a 3 and we're going to need an x. So let's put that up there. And let's go ahead and distribute that 3x. So 3x squared plus 12x. And then we change the signs and we add. The x squareds will be gone. We have 7x minus 12x, which is minus 5x. And then we bring down the next term. And we start the process over. So we go back over here to our x plus 4. And we think, how do I get that x to match a negative 5x? Well, I'd have to multiply by negative 5. So go ahead and put that up here. And that will give me negative 5x minus 20. And as you're writing it down, you realize, oh, yep, if I change the signs on that, remainder of 0. So that means 3x squared plus 7x equals 20 can be found by taking x plus 4 times 3x minus 5. So finding the product of x plus 4 and 3x minus 5 will give us that exact polynomial. Now, that's an okay process. It works pretty good. This process can be quite helpful for polynomials of degree 3 or higher. We can find factors, zeros, and x-intercepts. So it's important that we see that 0 so that we'll know, hey, we just found one of the x-intercepts. Now maybe we can work this down to something that will be factorable for us. Because again, what we know is that we can factor a lot of them, but that's mostly because the book gives us really nice ones. We can solve them by completing the square or the quadratic formula. But what we want to focus on now is how do we get the nice ones? And if we have something with an x to the 4th and it has more than 4 terms and we're out of methods for factoring, then how could we find all of those factors? So we're going to use the fundamental connections for polynomial functions, and for a polynomial function f and a real number k, the following statements are equivalent. X equals k is a solution or a root of the equation f of x equals 0. It is also a 0 of the function, which means graphically it is an x-intercept. And then finally, it means that x minus k is a factor of f of x. So that remainder of 0 that seemed like kind of a minor thing is actually pretty doggone big. So x minus k as a factor is a special case. And it says, do you remember another method to find both quotients and remainders without long division? And hopefully, you remember synthetic division. Also, the same method is called synthetic substitution. So synthetic division. Now, we can only use it when we are dividing by an x to the 1st minus k. That's when we can use this. So in the first example here, we see stage 1, which is using long division. And it just goes through the steps that we were using when we did long division. And for stage 2 here, what they did was they removed all the variables because that's an important part of synthetic. And then you see in stage 3, we have that collapsed vertically. Now this book is a little different in that they go ahead and make a little box in the upper left-hand corner for that 0 that you're trying to test out. So notice this was x minus 3, and what we did was we changed that to just the 0 that we needed, negative 3. And then we're just taking the coefficients of this polynomial. They have to be in order, and if anything is missing, we have to put a 0 in its place. So we have 2, negative 3, negative 5, negative. Use that to divide synthetically. So in stage 4, we use synthetic division. And with synthetic division, what we do is we start with that leading coefficient of 2, bring it down. Outside the box you multiply, and then you go inside the box, and then you add. Outside the box you multiply, and then you go inside the box and you add. So we're always adding down this way. And 3 times 4 is 12. You're back inside the box, you add, and you get 0. Now what's important here is that we remember the order for writing the answer to this, because it's always the remainder, then it's the constant, then it's the x, then it's the x squared, etc. as you move to the left. So you always start with remainder, constant, and then increase your powers of x. So 2x squared plus x plus 4 would be our quotient. And this, I just refer to this as math magic because it sure is a lot nicer than doing long division. I mean, it's called long division for a reason. It takes quite a while. So using synthetic division, this time it says divide 2x cubed minus 3x squared minus 5x minus 12. And we're going to go ahead and divide that by x minus 3. So the first thing I ask myself is, well, can I use synthetic? And absolutely I can use synthetic because this is that form of x minus 3. And when we're done, it says write a summary statement in fraction form. So we want to see what happens here. Now for x minus 3, k would be 3. And we have our coefficients. We have to make sure they're in order. If anything's gone, we put a 0 in there. There's a 2x to the third, negative 3x squared, a negative 5x, and a negative 12. So those are ready to go. You bring down that leading coefficient outside the box. And outside the box, we multiply by whatever's in this little upper left-hand corner. So that's going to give me 6. It's always outside the box, outside, inside, outside, inside. When you're inside, you add. So negative 3 plus 6 is 3. We're outside the box, multiply. Inside the box, add. Outside the box, multiply. And this one is telling us that our remainder of 0 means that we actually found a factor. Now again, what we have to do is figure out how to write our answer. So we have remainder, constant, x and x squared. 2x squared plus 3x plus 4 would be our answer. So like it said, write a summary statement in fraction form. We really don't have any fractions to put at the end, and that's because we don't have a remainder, which is what we like to see. Now, it says, obviously, we would love to use synthetic division all of the time. Why can't we? Because not everything that we try to divide by is going to be x minus k. If we have to divide by 2x plus 4, well, we're in trouble. We can't use something that has a number in front of the x with synthetic division. So that would be out. It's not that we couldn't divide by it. We could use long division. It's just that we're not going to be able to shortcut it with synthetic. So in order to use synthetic division, the divisor must be in the form x minus k. Has to. So we come down here and it says 2 polynomials are given. Use either synthetic or long division to divide p of x by d of x and express your answer in 2 ways. And so we have the first way where we write this as, all right, we've got our divisor times our quotient plus the remainder. And then the other one is the old-fashioned way you've used forever, which is, oh, here's my answer plus the remainder over the divisor. So when I look at A, it makes me really happy that this one is in that form x minus k, because that means I can take the 0, which would be 1, and I can divide this synthetically. So I'm checking right now to see 3, 2, 1, 0. They're all in the right order. Nothing is missing, so I don't need any zeros as placeholders. 1x cubed, 4x squared, negative 6x, and 1. Make my box, bring down the leading coefficient, multiply outside the box, and put the answer inside. Add inside the box. Now I'm outside the box, I multiply by 1. Inside the box, add. Finally, multiply by that 1 again, outside the box, and add, and we get a 0. So what this means is we have to go back and say remainder, constant, x, and x squared. And say, okay, well, what we just got for our answer was x squared plus 5x minus 1. So that's going to be basically the answer when this is a division problem. But we still have the 2 forms that they want this to be in. And the first form is, okay, if you wanted to get it back, How would you? Well, if we wanted to get this back, we would have to take x minus 1 times the answer that we just had. And when I say get this back, I mean, up here it did say, we should put d of x plus q of x plus the remainder of x. Normally, we wouldn't even bother putting this 0 here, but because I want you to be able to see that in the notes, just know that normally we'd say, well, if the remainder is 0, I'm not even going to put that on there, and we would take it off. And then we have the old-fashioned way that we used to do this, which is to write, hey, it's x squared plus 5x minus 1. That's what we got for an answer. And again, we know that the remainder would be 0, but we don't put that on there. That's just silly. That's a part of what we could simplify out of there. So there are the two different ways that we could write our answer. Now, I'd be really, really happy if I could also do B that way. Unfortunately, can't do it. And that has a 2 in front of that x. So that's the reason that I have to go with long division on this problem. So we've got 4x cubed, 0x squared, 7x plus 9. And I have to figure out, how many of those can I get in there. So I've got my 2x plus 1. And I only focus on the first term. So I think, how do I get 2x to be 4x cubed? I have to multiply that by 2x squared to do that. So I'll put my 2x squared up here. Now I actually do the distribution and say, all right, so I'm going to have 4x to the third plus 2x squared, but I have to change the signs and add. So 4x to the third will be gone, but I'll have negative 2x squared, and then I bring down that next term to try to keep going here. And I'm back to my 2x plus 1. And thinking, how do I get 2x to be negative 2x squared? I have to multiply it by a negative x. So that would give me negative 2x squared minus x. I'm going to go ahead and put my minus x up here. And then I have to change the signs and add. Well, my x squareds are gone, which is exactly what I wanted here. And then I have 7x plus x is 8x. And bring down the 9 and get back at it again. So now I have 2x plus 1, and I'm trying to match that 2x up to an 8x, so that's going to give me a 4. So I multiply by 4, and I get 8x plus 4. And I change the signs and add, and I find my little remainder of a 5. So now I have to write this one two different ways, just like I did the other problem. Let me see if I can scoop this down just a bit. Pardon me. So the first answer would be, hey, this is what I just got. 2x squared minus x plus 4 plus 5 over 2x plus 1, the divisor. So that's the way we've always written these in the past. Now, if you wanted to check this, you would have to take 2x plus 1 times the new information we just had, 2x squared minus x plus 4, and then you would have to add the remainder of 5. So we have that written in the two ways that this problem could be written. Again, the first one is where you're saying, you know what, if I were to work backwards, how would I get back to 4x cubed plus 0x squared plus 7x plus 9. That's this one right here. And then our second one is just the same as you've always learned before. That really isn't anything new to you, the fraction form. All right, so polynomial form and fraction form. And down here it says, real zeros of polynomial functions are either rational zeros or irrational zeros. So with the first one, we see, if we factor this, we get 2x plus 3 times 2x minus 3. And we set them equal to 0. Subtract 3, divide by 2. Add 3, divide by 2. And we have two rational zeros. For the second one here, x squared minus 2, and normally we wouldn't even factor this. We'd say x squared minus 2 equals 0. I'm going to go ahead and add 2 to both sides. And then I'll take the square root, so plus or minus the square root of 2. But it absolutely could be written in factored form that way. And that does give it irrational zeros. So if we had to write it in factored form, we could do that. And then we have the rational zeros theorem. And the rational zeros theorem is talking about how we are going to find all of these. But this will be a good place to stop and hang on until Monday for the rest of this. So, let's see. You should be able to make it through 2-4 day 1, number 1 through 26, with what we have so far. And then we will begin with the rational zeros theorem on Monday.